Okay, so let's start this series solution again. So again, to introduce this subject, let's just say you have y double prime minus 3x y prime plus 2y equals to 0.
From last time plus.
So this is the case where you have coefficients that are not constant. See, so far we were doing constant coefficient, second order linear, homogeneous or non-homogeneous differential equations, right? Yes.
Is this supposed to be the same one we did last time, or different?
It'll be very similar, yeah.
Oh, very similar.
I want to start over again. Okay. So if it's not a constant, then none of the methods that we were using so far will work. In fact, the solution of this differential equation will be so complicated, you can't really write down the solution in terms of basic functions. By basic, I mean exponential functions, sine or cosine or polynomials. You know, you can make new functions out of the whole by, if you have two functions, you can add them, you can subtract them, multiply or divide. You can even do a composition of functions, right? Sometimes you can take the inverse of a function. You can do all kinds of things. And therefore, if you just have polynomials, exponential functions, logarithms, trig functions, inverse trigs, these pretty much can create millions, zillions, infinitely complicated functions by doing all these operations, right? But still, none of them will be a solution to this differential equation. And therefore, the approach to this would be completely different. Rather than trying to go for the solution as some known functions, you're just going to say, I'm just going to go for the series, power series expansion of that. Okay, so remember, any analytic functions, the functions that we know have power series expansion. So e to the x is like 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus da da da. And I mean, you're trying to express an exponential function in this way. And it is really true that this equality holds. For example, if you plug in 1, and if you plug in 1 on the other side, it's really saying for x equals to 1, e to the first power is 1 plus 1 half plus 1/3, 1/6 plus 1 over 24 or something. And see, this is 1 plus 1 is 2, that's 0.5, that's 2.5, this much, and this is 0.166, and then what is this? This is like 0.04 something, right? So if you add this plus this is like 0.2 plus 2.5, that's 2.7 something, and the exact value of e is 2.71828. So they do match, okay? So you can actually compute. So if you wanted what e squared is, then you can plug in 2 and compute the right side to get this left side. And this is called the Maclaurin series or Taylor series. You learned it during the calculus. The nice thing is that if you know that the solution is a smoothly varying function, then you can represent that unknown function by some of these series. You can basically think of the solution as some infinite polynomial. So you can think of it like, oh, the solution of it, this is like y equals to a0 plus a1x plus a2x squared plus a3x cubed, and it never ends. By the way, do you know how we get 1 over 2 factorial all these? you can figure this out by just setting e to the x as a0 plus a1x, a2x squared plus a3 x cubed. See, e to the x is a polynomial that increases faster than any order polynomial. If you compare e to the x with, say, x squared, they both increase, but e to the x increases much faster, right? So you can, basically the idea is this. If e to the x is stronger than any other polynomial, why not think of e to the x as some infinite order polynomial? So you write it as a power series that never ends, right? And then to figure out what a0, a1, a2, a3 are, you just plug in x equals to 0, and you get e to the 0th power is 1. On the right side you get a0, but anything that has x in there will give you what? 0, right? So that immediately gives you that a0 is 1, right? And if you want to get a1, what you do is you differentiate both sides. Differentiating e to the x gives you e to the x. If you differentiate this, you get a1 plus 2a2 x plus 3a3 x squared plus plus. And if you plug in 0, you get 1 equals to a1. So you get a1 equals to 1 again. You differentiate again, plug in 0, you get a2 as 1 over 2. Differentiate, plug in 0, differentiate, plug in 0. That way you can get all these values, and it will turn out that it has a pattern. It's like 1 over 1 plus 1 over 1 factorial, 1 over 2 factorial, 1 over 3 factorial. And that's how it goes. That's how you get this, okay? And so that was what you learned as a Maclaurin series. It's that if you have a function which is differentiable infinitely many times, you can do this to figure out all the coefficients. Actually, I'm saying something slightly wrong. It has to be something called analytic to be able to get this expansion, but we're not doing math class for math majors here, so I'll just say if something is infinitely differentiable, you can do this process to figure out these constants, right? And what we're doing is we're working backwards. Let's just say we write down the solution in this form, and we're just interested in what these a0, a1, a2, a3 are. And if it turns out that these coefficients are coefficients of some known power series, like if it happens to be a0 is a-n's are these, then we know that the answer is e to the x. If it happens to be the coefficients of sine x or cosine x, then we would know that that's the solution. But most likely what's going to happen is that it's not going to match any of the power series expansion of the functions that we know. So you have no choice but to represent it as a power series. That's it. That's all you can go for. Okay? So that's why series solutions are needed. When you're working with non-constant coefficient differential equation, then it's really hard to go for any known functions, and you just go for something like this. It's not too bad though, because it's still, if you have a power series solution, you can still calculate the values of the function, right? I mean, just as how I showed you how to calculate e to the first power by doing the power series, you can do that. Once you have it, you can get the value. All right, let me just add two more initial conditions, and we'll try to find the solution. Let's just say y of 0 is 1 and y prime of 0 is -1. It could be anything else, but let's just assume that this is the given one. And we will try to find the solution in this form. Now, it's more convenient to write down sigma n from 0 to infinity of an x to the n rather than writing this all the time, especially when you try to do computations on the left side. You have to, in order to plug in y into the left side, you have to find the first derivative, second derivative, and also you have to compute the left side. So trying to write all this all the time is too cumbersome. You don't want to do that all the time. You really want to just play with this. So this is the shorthand for the left side, which means the following. when n is 0, this is a0 x to the 0th power. What's x to the 0th power? 1. So you get a0 times 1, which is exactly the same as this one, right? And then after that, you increase the number, this thing, so it becomes 1. The number after 0 is 1, right? So when n is 1, what do you get? a1 x to the first power, which is exactly a1x, right? And then the next number is 2, and becomes 2 to a2 x to the 2, x squared. That's a2x squared. And then when n is 3, you get a3x cubed, so you get that. And this summation, sigma, means you're adding everything that's produced by this factory. So it's like a factory that makes up terms with various values of n. And this sigma means after you make them, you produce them, you have to add them. That's what it means. Okay, now what's y prime then? If you differentiate, a0 becomes 0, this becomes a1, this becomes 2a2x, this becomes 3a3 x squared plus da da da. Now let's try to see how you can write it. It's always, if I say 3 is the n, that number is here, here, and this is 1 less than this number, right? So I can say n times an, and then this is 1 less than this number, so you should do 1 minus n minus 1. And then when does this summation start?
1.
N equals to 1. Now it doesn't hurt to say n equals to 0, and because if n is 0, then you get 0 times a0 times something, and 0 times anything is 0. So that's still fine. However, this will make the computations better. Now we will be going to over something called Frobenius Method. That's for the case when you have something called singularity. We will talk about that later. In that case, you will have to start from 0 even if you differentiate. And but for this case, for the simplest case, you just want to start from here. Okay. Now once you express the derivative and compare it with the sigma notation before, you see that you could have just went from here to there straight away, right away, just by differentiating x to the n. Because if you differentiate x to the n, it's n times x to the n minus 1, right? The only difference is you just have to remember to start from 1, because if you start from 0, the very first thing that this produces is 0. Okay. All right. Now, what's y double prime? Since we learned the lesson, we will not bother to differentiate this, but just differentiate this. So if you differentiate x to the n minus 1 comes forward. You get n times n minus 1, and x to the n minus 1, n minus 2, by the way. And n should start where?
2.
Start from 2, because if you start from 0, this will be 0. If n is 1, n minus 1, when you have n equals to 1, 1 minus 1 will still be 0. So n equals 0 and 1 doesn't produce anything, so you start from n equals to 2. Okay. And for the series solutions, this will always be the case. So maybe we should just write it down here, that if you set y as sigma n from 0 to infinity of an x to the n, then the derivative is sigma n from 0 to infinity n times an x to the n minus 1, and y double prime will be sigma n from 0 to infinity n times n minus 1 an x to the n minus 2. Okay? So that's always the case for basic series solutions. When we get to Frobenius solutions, it'll be slightly more complicated. But this is what we're going to work with now. Okay, now what do? Now you plug everything to the left side, and we just calculate. So, I mean, if you just accept that this is always what we start with, there's nothing here that's hard, but soon we will reach a very critical point, and that's the place where you have to watch out for. Okay. So right now we'll just plug everything in. So y double prime is sigma n from 0 to infinity n times n minus 1 an x to the n minus 2 minus 3x sigma n from 1 through infinity n times an x to, oh, this doesn't start from 0, it starts from 2, n minus 1, and then plus 2 times sigma n from 0 to infinity an x to the n has to equal to 0, right? So that's why you get in the left side if you actually plugged all these into the left side. Our goal is to make this 0 at some point. Okay? Now what we're going to do is although this shorthand is convenient to write, it's better than writing plus, 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 and dot, dot, dot all the time. It's a lot easier than that. It also saves paper, so it's green, right? It's energy saving and all that. Yes?
Why did those start at 2 and 1 opposed to 0 again?
Oh, why did I put that 0? It should be 1 and 2. Yeah, so I was explaining that if you plug in 0, it doesn't produce anything, so you start at 1. And when you start from, this one you should start from 2 because 0 and 1 produces 0. Okay. Thank you for pointing that out. Okay. Okay. So that's always the case. Always use these. Plug it in, and we will try to simplify. So although it's convenient to write the sigma notation, it's good for the environment, but the problem is once you write it in a shorthand, you forget what it was, and you lose that intuition of what you can do. So you really need to be able to go back and forth between the two notations. So what is this? This is a bunch of terms added up, right? And you're multiplying something in front. What can you do? You can multiply this to inside, right? That's called distribution. Distributive law enables you to say this can be multiplied to inside. And that's what we're going to do. We're going to say plus sigma n equals to 1 to infinity, negative 3 nan, but then I can say x times x to the n minus 1. What's that? This is x to the first power, x to the n minus 1. If you multiply them, what do you get? X to the n. X to the nth power, right? So you get x to the nth power. And you can do the same thing too. 2 times this huge summation can be expressed as, you can multiply the 2 to individual terms. So you can have 2 an x to the n. So that's the first thing that you have to know, the fact that anything multiplied you can put it inside. That's the first thing that you have to know, which is kind of obvious if you know what this sigma means. But here comes the hard part. The hard part is, the first hard part is, I want to put everything together in order to simplify things. And in order to do that, you will find out that you really want to make this exponent the same. So basically, you want to collect the like terms, and in order to collect the like terms, the exponents must be the same, right? So if this is x to the nth power, here you have n minus 2 power. Right? In that case, that's not good. And therefore, you do something called shifting. And shifting is the most basic tool that you need to know how to do. So let me try to explain this thing called shifting. What is the shifting? Shifting. What you do is you replace this n by n plus something or n minus something so that everything will have the same exponent. Okay, that's what it is. Now, since this has x to the n, that's x to the n, I want this to be x to the n. So you want to replace n by n plus what?
2.
N plus 2, right? If you replace n by n plus 2, this becomes n plus 2 minus 2, so that becomes n, right? And once you figure out what you have to replace n by, it should always be n plus some number or n minus some number, only integers, okay? Then you have to change everything else, all the n's that you see, even this n. I see an n here, 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 here. All these n's must be replaced by what you need to do. Yes?
You just do that in the one that doesn't have the common thing?
Yeah, so if you have maybe 3 terms or 4 terms, maybe 2 of them have the same exponent and the other 2 doesn't, then you change the ones that don't agree. Okay, so it's not always x to the n. Sometimes 2 of these summations would have n minus 1, then you would want to change the other one as n minus 1. Okay. Okay. So let's do that. Shifting. This is the most important thing that you have to understand when solving using the shifting. Okay? So first, what should n equals to 2 become? That becomes n plus 2. See, you're replacing n by n plus 2, so I replace this n by n plus 2, and that's equal to 2. But what does that mean? That means n is 0. That's what it means. N equals to 0. Okay, and then what does this one become? Let's see, that becomes n plus 2. N plus 2 minus 1, what's that?
N plus 1.
N plus 1. And then a sub n plus 2. So this becomes n equals to 0, that becomes n plus 2, n plus 1, a n plus 2. That's what you have, okay? So after doing this shifting, here's what you end up with. You get sigma.
Wait, you have
You didn't shift the x.
the n to the x still, right?
X to the n plus
Yeah, x to the n plus 2 minus 2, that will turn into x to the nth power. Okay? So this is what you get after the shifting. N starts from 0 to infinity, and you get n plus 2, n plus 1, a n plus 2, x to the n, and the other ones, it stays the same. You do sigma n equals to 1 to infinity, and then minus 3n an x to the n plus sigma n equals to 0 to infinity 2an x to the n. That's what you get after doing the shifting. Any questions? Yes.
You've only got 7 minutes left on this recording, so should I stop and start it again?
Yes.